Okay, so here we are. We're going to look at the code in the model um, and see what happened. This is once again the New Jersey model, so you can see the early peak in infections, followed by the kind of the steady state in infections that goes on for a long time. Okay, so in order to run this model, we had to do a couple of things. Okay, first of all, I did something to make the model easier. I got rid of the hospital threshold that we had in there. It got rid of a couple of lines of code. And the reason I did that is because it doesn't seem like any state is going to actually exhaust their hospitals. It seems like as soon as the hospitals are filling up, that's when states get tough and put in restrictions and lower and get the curve to flatten. So no one's really going over that hospital threshold. So it makes sense to remove that from the model to make the model a little bit simpler. Okay. The second thing I did change though is that I made B go to 1. Okay. Instead of having it be 0.5 as it was before. It seemed like our model was laggy. And when we look at the data, what it seems to be is that when somebody gets exposed, usually this 1 in the denominator means 1 per 1 week. It means that in about 1 week, most people would have gone from being exposed to being infected. Okay, so it seems like it can go as long as 2 weeks, but the majority of people, once they're exposed to the virus within a couple of days to a week, most of them will have become infected if they're once they've been exposed. So that's why I changed that number to 1. Now, when I changed that number to 1, I did have to reset all of these A values and my I0 value to get a new data match, right? So in order to get the data to work for deaths, remember we have an ever increasing amount of data for how many people have died in New Jersey. We take a weekly reading. We can match that based on the change to the model. Okay, so that was an important change, I think, to make it more realistic. I also don't know that we have a 6-month immunity, as we had talked about in the last model. So I changed this down to, instead of being 1 over 26, 26 means that most people will lose their immunity in about 26 weeks. Now we're saying most people will lose their immunity in about 17 weeks, all right? Now, if we look, we'll play around with that number in a moment to see what happens when we change that. And then we have to have 2 death rates. Okay, the original death rate, about 0.25%, and a death rate for the second time around, which is about 0.1%. Okay, so those are the parameters that need to get changed. And then as we go down into our vectors, notice we have an S1 and an S2 now. Okay, so S2 is the susceptible people who have already been sick. E2 needed to be created. Those are the exposed people who were already sick in the past, so they're going to have those T cells. I2, infected people who were infected in the past. Okay, we only need 1 state variable for R because recovered people will always go back into S2. Doesn't matter whether they came from I1 or the first I or the I2. They will, since they're going to go back to the same place, we don't need an R2. And obviously when people have died, they will stay in that category. So we don't need a second category for that. Okay, so going down, so there are a lot more state variables now because we've doubled some of them up. Okay, now as we go through this, other changes are, we have to change S and S2. Now before we just said S was everything that wasn't E, I, or R. Okay, now I'm actually going to have a change in S that gets calculated by the A, I. Now notice for the I's, I've added the I1 and the I2 times S. So in the differential equation, dsdt will be AIS with a negative in front because they're leaving the susceptible pool and entering the exposed pool according to this equation. Okay, and then the second line here, you've seen lines like this. We simply take the infection, or I'm sorry, the susceptible population, and then we add the change, which will be a negative change, which will cause it to go down, right? Now we do exactly the same thing for the second susceptible pool. People will leave that according to AIS. That's what this is all about, A, and then we have both I's and an S, but they're entering it according to DRDT. Okay, so we do have a, the coefficient D times the number of people who have recovered already. That's going to determine how fast people go back into the S2 pool. And then the next line of code is just adding the changes to the S2 pool to what was already there. Okay, now we do the same thing for E, and that's determined by AIS going in minus B times E going out. And we have exactly the same thing down here for the second exposed category. So we have 4 lines of code for E, and then we have 4 lines of code for I. Remember, BE goes in to the infected pool, and CI is coming out of the infected pool. We just add the changes on in the next line of code, and then we do the identical thing for the second infected pool. And then we're down here to R, and we know that 1 minus dr. Oh, okay, so this is because the death rate, which is a small amount, so 1 minus the death rate is still about 1, but the death rate will depend when you look at this. Oh, we also have a death rate 2 here. Okay, so this is the first death rate with the first infected pool, and then we're using the second death rate with the second infected pool, and then these are the people who are leaving the recovered pool. That's why there's a minus sign here, and going back into the second susceptible pool. All right, and then we add the changes onto what already existed. And then we have, for the deaths, we do a similar thing, except we use the death rate instead of 1 minus the death rate. So if 1% of the people are dying, 1 minus DR would be 99% recover. And this would be the death rate times the number of infections with a C thrown in there to show how fast it's happening. Okay, so we're basically splitting the people coming out of the infected pools into those who have recovered and those who have died. Okay, and the death rates are lower percentages, so most of them will recover. Right? Then there's a little bit of code down here. For graphing purposes, I want to know what the total susceptible population is, which is a combination of the original S's and the second pool of S's, the total exposed population, and the total infected population. So I have those things in there. And then I made a couple of changes in the plot. When I'm plotting the susceptible population, I have 1 line for the total susceptible population and another line that only shows the people who are susceptible who have never been sick. I did the same thing when I get down to case 3. Instead of only plotting T and I have a total infection, and I have I, which is people who are infected the first time. We plot both of those lines so we can see those simultaneously on the graph. And the other things remain more or less the same, except that we aren't plotting the hospital threshold line in there. So we removed anything about the hospital threshold. Okay, so those are the updates to the code that make the model work according to the changes in the model. So it allows for people to get sick more than once, but it makes them less likely to die from the coronavirus. Okay, so we didn't have a line for hospitalizations or anything else, but the line for deaths and the line for hospitalization should somewhat be in proportion to one another. So as the rate for deaths goes down, so should the rate for hospitalizations. So we should have less stress on our medical resources over time. So this, I will also post the code itself the newest version of this in the assignment when I post this video.